Okay, well, I'm the Senior High Performance Computing Specialist at NCI, which is based here on ANU campus. I've been running and using compute clusters for about 15 years now, and at that GitHub URL there is most of the source that I talk about in this talk, and a bunch of other stuff too that I don't have time for. So what does the HPC Systems Specialist do? Well, basically, I boot, run, monitor, improve, develop the kernels and file systems on all our high-performance computing clusters, supercomputers, HPC clusters, same thing. And fundamentally, I just try and make all our toys run better. So there's lots of interesting talks about Linux on little toys like this, and I guess this is the other end of the scale, fairly big toys. So does anybody remember when people used to have matchboxes and they used to put a matchbox in the corner of the picture to set the scale of the picture? Well, this is a Linux talk, so obviously we're going to have a standard Linux Penguin as the matchbox instead. So there'll be some slides that use this as a scale reference. Okay, so here at NCI, we're one of the few large high-performance computing sites in Australia. There's about 3 sites now. Typically, we do have the largest machine in Australia, the highest on the top 500 list, but machines become small very quickly in the high-performance computing game, and so all the 3 sites are probably leapfrogging each other over time as we all buy new machines. So what's running on the machine? It's for all Australian researchers, and there's basically an awful lot of science is done. We have a focus on climate. The bread and butter size of compute jobs is about 256 cores out to about 1024 cores. So they're the sort of jobs that are all routinely running on the machine, doing the sort of sciences. Currently, over the last about 5 years, we've been buying mostly 64-bit InfiniBand clusters, and the economics of how much money we have to spend and the size that we are as a supercomputing site, that trend seems unlikely to change anytime soon, which is awesome news for us, really, because it means we can build something stable and keep moving along with it. So this is our current production machine. It's called Vayu. It's about 3 years old now, and it's 1,500 nodes. As you can see, the ceiling is quite low in our old data center. This has actually been a really very good machine, although to be honest, it was better when it was a Sun machine than when it became an Oracle machine. The problem with Oracle is getting hardware replacement parts out of our mate Larry. It's quite difficult now. So this is a new machine that was installed about last September, and it still isn't running yet. The vendor's still sorting out a bunch of broken bits with it. We've got access to a tiny part of the machine to do some testing on. But actually it sort of doesn't matter because the machine itself is fairly unexciting. Most aspects of it are just straight the same as our current production machine, just scaled up with about 2 times the money to spend on this guy. And it's got technology refreshes in almost all the components. So from a software point of view, it's fairly boring. So Vayu is about 1,500 nodes. The new machine goes out to 3,600. So this is where the 3,600 penguins in a room and my talk title comes from. Though actually, if you include the Linux instances that are running all the management cards on these nodes, and includes the management server and stuff, it's more like 8,000 Linux instances in a room. And if you're counting boot penguins, it's about 60,000 boot penguins. So we're going from about 12,000 Halem cores to about 58,000 Sandy Bridge cores with a much lower gigahertz. But actually these cores are around about the same speed, plus or minus the games that people play with compilers, and that the newer compilers on the newer cores make the newer cores look a bit better than they really are. We've got about 6 times more effective work being done on this new machine for about 3 times the power usage. And really, the sort of fundamental hardware change on the new machine is that we're getting better power efficiency out of it. Apart from that, it's really not that different to the old machine. So some other big numbers, we'll get these out of the way. We're going from about a 1 petabyte Lustre file system on the old machine to about 10 petabytes. It's about 4,000 3 terabyte disks in the new machine. So who knows what Lustre is, the Lustre file system? Oh, that's awesome. I barely need this slide at all. This is a Lustre 101. Yeah, it's a big distributed file system. I never know whether to call it a global cluster or a distributed file system. Not quite sure what the difference is between them all. It's on most of the top fastest HPC machines in the world, and the current record is about 1 terabyte a second of bandwidth from the Sequoia machine at Livermore. We've been running Lustre on all our big clusters for about the last 6 years now. And people say it's kind of hard to run, but since the whole Oracle thing, basically I've been a Lustre support contract. So frankly, if I can do it, it can't be that hard. So yeah, we're going from about 1 petabyte to 10 petabytes of Lustre. We're going from about 20 gigabytes a second file system to about 120 gigabytes. Something that is a fundamental change from the old machine to the new machine is that we run software RAID on the old machine and we run hardware RAID on the new one. We're big fans of software RAID. It's really transparent and clear. It's a bit slower, but we have sort of great confidence that if we have like a triple disk failure in a RAID 6, then we can probably ram it back together and it'll lose only a very little bit of data with software RAID. With hardware RAID, it's expensive, it's a black box. It does run a fair bit quicker, but I guess we just don't know if we're going to be able to get any sort of disaster recovery out of it. And it's a bit of an experiment. So the other thing is that Lustre scales horizontally perfectly well. So for the additional price of hardware RAID, you could have bought more software RAID. But anyway, this is a machine we have, and so we were trying out hardware RAID for a while. So this is the bit of infrastructure that actually makes this a supercomputer and not just a pile of servers in a room. So this is one of the core InfiniBand switches. We have 6 of those on the new machine. It's a full non-blocking fat tree InfiniBand fabric. And turns out that latency is extremely important for supercomputing. And this is one of the lowest latency networks you can get. It's 1 to 2 microseconds latency user process to user process. And that's about 25 times faster than GigE. Not to mention that you can't buy a GigE switch this big. So the bandwidth also goes up, and that scales up with about the horsepower on each node, so that all works quite well. So what does a full fat tree give us? Well, it means you can run a single job over most of the cluster, and you can do the really big science that we want to do. Low latency, like I said, it's important for this strong scaling case where you're just throwing more cores at the problem. As you scale that up to more cores, you're using smaller and smaller messages, so you become latency dominated. Some codes which just scale up the problem size as they add more cores, bandwidth can be important for those, not all of them. But so latency is a real killer, and that actually is one of the things that hasn't changed from one cluster to the next, and it's sort of not likely to. There's sort of physics that gets in the way of doing much quicker than that sort of latency. So in my opinion, actually one of the best things about the new machine isn't the new machine at all. It's actually a part of the building. So this is a free cooling heat exchanger. It's a big plate and frame heat exchanger. Google's got hundreds of these things, and we've got one of them now, and we're very happy. So these green pipes go up to the cooling towers that live on the roof. These blue pipes go into the machine room. And inside the machine room, we've had this technology for several generations now. The basic idea inside the machine room is that you have sort of car radiator style things that either live in the rack door or in row, and the car radiators in reverse. So you blow lots of hot air from the compute equipment over them, and you run cold water through them, and it goes out the back through the heat exchanger in this case, and then you get rid of all of the heat that you dump into the room. So this talk is really just an excuse to show penguin pictures, but anyway. So you don't actually have to live in a really cold climate to do free cooling. You don't have to be at super high altitude where it's cold and dry either. And in fact, if you go to this sort of high Atacama desert, then the air is actually too thin to do the air cooling part of cooling the compute blades down. So it turns out Canberra is actually pretty good for free cooling. So this graph, we did some sums before we decided we wanted to do this. So this is what's called wet bulb temperature. This is the temperature at which cooling towers transfer heat to the air. And this is percentage of the year at which we're below this temperature. So if we want to send 18-degree water through our computer, then we lose about 2 or 3 degrees across our cooling tower and across our heat exchanger. That's mostly approach temperature, what they call approach temperature of the cooling tower. And it means that for 80% of the year, we can actually run just on free cooling towers, which is, we thought was quite amazing. So what does free cooling actually mean? It means we just run a pump around the water loop in the room, another pump to go up to the cooling towers, and we run some fans on the cooling towers, and that's the only electricity we use to get rid of all the heat in the room. So it means we're not running chillers. So for 80% of the year, that's what we can do. For some other small percentage of the year, we can go into some hybrid cooling mode where we run a little bit of chillers and still run the free cooling, and then the rest of the year we're just using chillers. So the name of the game is to try and raise the water temperature that's going through the room. So this means finding all the hot spots across the equipment and eliminating all the air leaks from all the different containment systems we have in the room. And if we can actually get the water supply temperature up to 21 degrees and still keep the computer equipment at a reasonable temperature, then we actually in Canberra we can get to about 95% of the year completely free cooling, which is hopeful. So yeah, we've been doing pretty well. We've had I can't actually remember what PUE means. That's a data center efficiency number. So it means that basically if we use 1 megawatt of compute equipment, we use 1 megawatt of electricity from computer equipment, then we spend another 0.1 megawatts on removing that heat from the room. So back in 2005, we were already at 1.2, which is fairly awesome by a lot of data center standards. And now we've dropped it to about 1.1, and we're hoping for maybe a little bit better. But the only real next big step, this is all sort of incremental changes, the only real next big step in cooling is to try and eat away at this big 1 number here. So that means that we try and actually sell some of the 1 megawatt of heat that we're dumping into the machine to the building next door. Obviously you need something that runs 24/7, and that's my favourite option, but I'm pretty sure it's not going to happen. Okay, so that's all the boring hardware part of the talk over and done with. So I'll just be talking about software from now on. So there's lots of really good open source software for supercomputers, and a lot of this has been around for a long time, and it's very well sorted out. So some people ask us why we put together our own software stack. Why would we do this? HPC vendors can certainly give you a software stack, and they can give you schedulers and installers and even some things with pretty GUIs on them. And the real reason for this is that we can do a better job if we do it ourselves. There's all sorts of details in the reasons there, but it sort of comes down to being able to upgrade and maintain the machine over time and provide the users a consistent experience. And it actually reduces our own effort, because every single time we get a new stack, we have to port all of our infrastructure around the supercomputer to this new stack, and that's really a lot of effort. So just having something that installs but doesn't really have a clear path to upgrade, which is a lot of these systems do, just really isn't enough. So yeah, we gather our own software stack. We make it of this sort of our version of the best of breed of open source software that's out there. So Lustre file system I've talked about a little already. We use this OneSys cluster management system. It's quite old, but very suitable for what we want. We write completely our own resource manager and scheduler. We use RHEL or CentOS. Actually, we use CentOS 5 and 6. OpenMPI is the library that actually every compute job that scales to more than 1 node uses OpenMPI. It's open message passing interface. Actually, that's how all the parallel codes work. They send little messages around to each other explicitly saying, byte A goes to machine B. Environment modules, Kevin Pulo from our site has been talking about sort of environment modules on steroids, his sort of SysX distribution. We use the sort of simplified, just almost regular modules on the supercomputer. We use Ganglia for sending a lot of data around. We don't use so much of Ganglia's intrinsic metric gathering stuff itself, but we use it more as a data transport mechanism. So most of those bits on the previous slide there, we actually have modified to some large or small extent to make them better. And we try and push all of those changes upstream where we can. So we also just quickly mention we also leverage some other really good software from the big US sites, but I won't really talk about that. So we've talked about Lustre already a little bit, and so we're going to the cluster management system now. So this is OneSys, and my basic philosophy is if you've got one machine, it's okay. If you've got two machines, it's a bit of a pain. If you've got more than 3 machines, then you definitely need some sort of a cluster management system to use it. And OneSys is the one that we chose for this machine, well, for all our machines, really. So specifically, if somebody gives you a large cluster, how do you boot and manage it? So OneSys handles applying different roles to all the different machines. It's not super suitable for if you have every node has got a completely different role or every node has got completely different hardware. It's not really designed for that. It's designed for something where you can put machines into big classes. So big chunks of your cluster are roughly the same or doing roughly the same thing. And OneSys is almost always run using a shared read-only root file system. So the basic mechanism for setting up a node role when you have a root file system that's mounted read-only is that really early in the boot stage, your etc. FS tab, which is a link into a little RAM disk. So this RAM disk is set up really early in the initial boot. That link points into it. The OneSys software, as soon as it gets hold of the node, then sets up a pointer, another symbolic link back to another read-only file in the root file system image. And so based on how this link back is set up, then it tells you what that compute node is going to be doing. So you can set up link backs based on, well, they're all based on host name, but then you can group the host names into hierarchical classes and set up link backs based on the classes. And you can also set little node property flags if you've got the occasional bit of hardware that's got something like a different disk array attached or something. So a bit more about OneSys. So you end up with an operating system image in a directory. You can just intrude into it and do things. There's one master text file that tells you all of the things you need to configure about OneSys. And that essentially points to all of the other little config files, like all of the other versions of etc. hosts or etc. FS tab that you want to set up in all the compute nodes with different roles. It's normally run with root on NFS, but because NFS sucks really badly, and in particular if you load it up with more than a couple of hundred clients, then it doesn't just go slow, it tends to actually pretty much stop working if you really push it hard at about the 200 clients level. So Lustre, we already have a big Lustre file system. It's very scalable, it's got failover, and it's really a no-brainer to say that NFS doesn't work, we'll just put it on Lustre. And Lustre does slow down as you add more things to it, but it degrades very smoothly and uniformly and never hits a wall like NFS does. So basically we end up with thousands of nodes that mount the same root file system from Lustre, and Lustre's client server caching really helps us a lot here because, so you're loading glibc, if it's not cached on the client, it'll definitely be cached on the server because it's a hot file, all the compute nodes are accessing it. So basically we never go to disk for the operating system, it's always cached in RAM somewhere. Yep.
If you lose power to your data center and everything reboots at the same time, how well does that work?
So it turns out that it's none of this stuff I'm talking about here is the limiter for how fast you can boot the cluster. It's getting the InfiniBand fabric stable is actually the limiter. You can only boot so many nodes at once on the InfiniBand fabric. So we tend to boot about a shelf at once, about 24 nodes at once, and basically takes most of the day to boot the cluster. Thankfully the power in Canberra is fairly reliable. This happens at most once a year. But it does happen when we get cooling failures, in particular cooling software failures. They tend to take us out and we come back. But we're not a bank, and we're trying to get the best bang for the buck. And so we make compromises like that. We have ways to solve this. There's on the new machine, we've been working with Mellanox to do some of the InfiniBand, or do all the InfiniBand, and they've got a system which is more scalable than all sort of tweaks to what we were using before, and we can probably boot about 500 nodes at once if everything works as it should. Okay, so we have a one-sys system, we have root on Lustre, it's all scalable, it's all easily to maintain, so now we can go to the beach. But, what's that? That's a seal. Don't seals eat penguins? Yes, we're in trouble. So yeah, this turns out there's more work to do. We essentially don't turn off old clusters at the moment, so what we do is we accrete more and more clusters, and so the same rule applies. One cluster is okay, 2 clusters is a pain. If I have to look after 3 clusters, I want a sort of a cluster of clusters management system. And it actually turns out to be really easy to wedge this into OneSys as well. So this is work I did in the last year or so, and it's now running on all our production machines. So there's, did I skip a slide? What happened? Oh no, okay. So on the init ramfs side of the 2 stages of OneSys booting, maybe I did skip a slide. Anyway, so it turns out to be pretty easy to add multi-cluster support. Basically, you just want to hack the /init file in the OneSys init ramfs, and you tell it which cluster it's booting on, and you tell it at a local IP in the cluster that it can talk to, and you set up sort of some extra files inside the init ramfs that are set up in the style of OneSys. So this is, the modules file we would load on cluster X. This is the modules file we would load on cluster Y. And you have the little bit of logic that says this is the cluster that's what I'm going to load. You also have to include a superset of all the kernel modules in the init ramfs, so it bloats out the init ramfs a bit, because now you've got NFS modules, lots of different network drivers for the different clusters, and all the Lustre stuff as well, but it turns out to be not very much. So on the operating system image side of OneSys, basically, there's nothing to do. From a hacking point of view, we don't have to change anything. All we have to do is rearrange things. So if we had an fstab.login for one cluster, now that moves to be an fstab.clusterx.login in the shared cluster image. So you basically merge all the separate configurations together and you end up with one big sysimage.conf file. So it's actually not that big because you're doing the same thing on multiple clusters, generally speaking. So yeah, it works pretty well. It's quite neat. So yeah, what we end up with is a single multi-cluster aware kernel, all of the kernel, the init ramfs and the operating system image, they just all boot on all three of the main clusters with root on NFS and on one smaller cluster with root on Lustre and on one small cluster with root on NFS. So now we really can go to the beach, and it's a much nicer beach without seals. So that was how you boot high performance computing machines, clusters. Running them, that's a whole different thing. The key line here is just being obsessive compulsive about things. So I won't go into all of this, but this is some of the stuff that we do. And it sort of comes down to, at the end of the day, you have to track down every problem you see, find a root cause, and make sure it doesn't happen again, put in checks for it. And a sign that you've done everything right is that you end up with, you're sending 1,500 nodes worth of varlog messages back to a single point. If you can read that varlog messages sensibly, it's not just line noise, it's not scrolling past at a vast rate, then you've done a good job. You've created a stable cluster and you'll be able to find new problems when they turn up. So why do we try so hard to be very careful about the cluster? Another way of saying this is, why is managing an HPC machine so difficult? And the reason is, well, we'll go through an example. If you have one code that's running on 2/3 of the machine, so it could be running a single code running on 8,000 cores, if one of those bits of hardware in any one of those nodes is running slow, your entire job runs slow. There's no escaping this. So it runs at the absolute minimum across all of the bits of broken hardware that you're running across. So it means that you're running a really big code, you could be wasting 2/3 of the machine for as long as that code's running. So the bigger your cluster is and the more parallel the codes that you're running on it are, the more of a problem this is. So what the upshot is that everything needs to be fast and uniform, and that we have real problems with hardware that's slow and erratic. If something's running at half speed, that's terrible, and we really, really, really want to turn it off. So there's plenty of use cases out there and plenty of people who manage servers, and if the server's still running, that's great. They don't care if it runs a little bit slower, and that's fine for them. In the HPC world, that doesn't fly. That's not what we can do. So slow and erratic hardware is terrible. We'd much prefer to turn it off. Okay, so this is a bit more, which is, I guess, verging on monitoring stuff. This is like a quick visual representation of a small part of our cluster. Each one of these little blocks is an 8-core node, and the coloured things running on it, they're some of the compute jobs. So I'm hovering over this red one here, and this is a 960-core job. That's a CPU it's using, that's a network it's using. So this tool is about 10,000 lines, I guess. It's about 5,000 lines on the server side that pulls together all data from PBS and Ganglia and all the metrics that we dump into it, and about another 5,000 lines of JavaScript in the browser just designed to make it, basically, most of those lines are there to make it go fast in really slow browsers. But still, I wouldn't probably go to that URL with a phone. It's gonna, it's gonna take an awfully long time to render that amount of compute nodes. So this sort of quick overview of a machine view has actually got less and less useful over time. The main reason for this is that clusters are now using InfiniBand, which means they're spinning in user space doing communication. So it used to be on GigE clusters, you could just look at a job and say, okay, there's idle time there or there's system time there, and that's the kernel either not doing anything or it's sending network traffic. And so you could just quickly visually look at a job and say it's load balanced or it's hung. These days you really can't. InfiniBand using RDMA means that if it's waiting for other cores to catch up, then they're just spin waiting and they're using 100% CPU time. You can't tell 100% CPU time spin waiting from 100% CPU time doing floating point operations and getting science done. So we've sort of been working on how to do this. It turns out the OpenMPI layer is about the right place to hook this into. But it's actually difficult to get this reliable and get the information out of the library and out of the user space, out of the user codes that are running, and to put it into the monitoring system. And it's also important that the OpenMPI stays completely stable and doesn't slow down at all. So the code has to be basically perfect before it goes in production. So it's quite a difficult problem. It's not prime time yet. So another part of monitoring a cluster is that there's, so this is live sampling of a file system. This is about 3 years across the x-axis, and this is speed up the side. This is one of our small RAID 1 file systems. And these points are basically showing how the speed of the file system has changed over time. So we're doing this sort of thing, actually we're doing this sort of thing mainly to check for silent data corruption. But a side effect of that is that we get speeds for all of the different components of the file system. Lustre is made up of like 104 different parts of the file system in the case of all our file systems on the current machine. And so this dark line here, set of dark scatter points, it's running on a live system, so it's always going to be scatter points. But they're showing that we've actually improved the file system performance at this point. We changed the software, we changed the hardware, both at the same time, unfortunately, so I'm not quite sure what did what. But anyway, so it's basically checking so that we don't go down over time. And it's the sort of thing you have to do because we can't really interrupt a production service and go and just measure everything and make sure every disk is actually at the right speed. We have to do something statistical on a live system, and it is actually fairly difficult. So another thing you have to do with an HPC system is deal with failures. We have a lot of redundancy in the machine, the network, 4 or 6 core switches, all of those except one can die and everything has still got full connectivity to everything else. But the file system servers can die and we can fail over to another one. The disks are all in RAID arrays. But you still have a lot of failures to deal with, and sometimes you have an unexpectedly large number. So this again is about 3 years across here, and this is the number of disk fails we get per week. And so we started off at like less than a disk fail a week, and now we're up at about 3 or 4, and like clearly this is going up into who knows where. So another point about this is that, well, we haven't lost data through disks failing. We haven't ever completely lost a RAID 6 or a RAID 1, but we are also very keen on now on RAID 1 triples, which we've used on metadata for the current machine, but we haven't used on data. But we're hoping to use those on the next machine. So another point here is that this is about 1,200 disks in this file system, and over 3 years we replaced about 250 of them. That's a lot. And if you look up the manufacturer's annualized failure rate for these things, it's about 0.73%. We're running at about 10 times that rate. So either these disks are really, really crap, or we're pushing them very hard. Either way, I wouldn't suggest you buy any Seagate 1 terabyte ES2 drives. Not that you can buy them anymore, so it's safe to say that. But. Okay, so back to our software stack, sort of had a monitoring diversion there. So this is about a scheduler and resource manager. So this has been written, it's a fork of OpenPBS, and it's been written in-house by one of our people, David Singleton, over about the past 12 years. It does suspend resume scheduling. This is its sort of, I guess, main killer feature. And suspend resume isn't anything magic. It's just sending sig stop to a process when we want it to stop and sending sig cont to a process when we want it to start. But it turns out that this very simple thing means that you get really high utilization of your hardware, and it also means that you can run a really wide and varied job mix. A lot of HPC sites restrict the wall times of jobs, or they restrict you to like greater than 1 node jobs because they can't handle some of the workload otherwise. We don't do that because suspend resume handles it for us. So this is the sort of utilization we get. This is just like recorded this a couple of nights ago. This is our utilization over the past months. This is the ganglia plot. So if you look at the average available nodes versus what PBS actually allocated on, we're running about 90%, 97% utilization on the machine. So that means 24/7 we're using 97% of our cores trying to do real work. Fine, they may actually be just spin waiting because the codes are terrible, but we can't do anything about that. But we're providing the maximum of the machine that we can to the users because the scheduler is doing a really good job. So this percentage is way better than what typically what's called backfill schedulers do. And that's the sort of scheduler that runs at most other HPC sites around the world. So suspend resume, so how does it actually work in practice? So for example, you have an 8,000 core debugging job that wants to run for 15 minutes. So what it does is the scheduler goes around and finds 8,000 cores of smaller jobs on it that want to run for longer than 15 minutes, and it just sig stops them. The 8,000 core job runs over the top, it does its thing, it gets off, you send a sig cont to all those little jobs underneath, and they all come back and they start off from exactly where they were. So it turns out it's not possible to run, it's extremely inefficient, let's just say, to run 8,000 core 15-minute jobs if you don't have a suspend resume scheduler. You have to create an 8,000 core hole in your machine to actually get that started if you don't do suspend resume. And okay, so you can actually sort of mix these style jobs with checkpoint restart, but checkpoint restart A doesn't work, and B it's inefficient. And it's inefficient because generally speaking, when you run this 8,000 core job, it doesn't do any I/O, or it does very little. When the job comes on, the operating system just pages out RAM if it needs it, and so it pushes these little jobs, which is suspended, it pushes them out to swap. But generally, the scheduler is able to find nodes that have sufficient empty RAM on them already that it doesn't even need to do that. So checkpoint restart involves saving the entire state of the jobs to disks. And so it does that every time, even if the job only runs for a second. So it's extremely wasteful. So suspend resume is in fact better than checkpoint restart. So David likens suspend resume scheduling to playing 3D Tetris in space and time with a wide job going for a certain amount of hours, but you can cheat in Tetris because you can cut all the blocks in half and make them fit around each other much neater. So the other killer feature of our resource manager is its extensive NUMA awareness. So we've been doing this for an extremely long time, since old machines now, but were much more NUMA than today's small NUMA nodes. So it's all very well debugged code. Uses CPU sets everywhere, and so that locks down part of it. It turns out the OpenMPI library, again, is a place to do a lot of NUMA binding and CPU binding, and we've worked with the OpenMPI people and got some patches in there. I think they had CPU binding, and now we've got memory binding added to it as well. And we run with this on by default. So the upshot is that we rely absolutely as little as possible on the kernel. So the fact that we're running 2632 vanillas or RHEL 6 kernels or even RHEL 5 kernels doesn't really matter, because we're trying not to rely on the kernel at all to get the NUMA affinity right. Okay, so kernels and operating systems. We really rely on being able to get into the kernel and fix things or work around things. So this is a bunch of random issues that we've fixed over the years. Some of these have taken like a week to find, and then, you know, a one-liner and just a day or so to fix. Some of them have taken months. But we do rely on it. So I'll just go through a couple. So Lustre sends 1 megabyte RPCs across a network to do its I/O traffic. Turns out that the standard Linux SCSI layer doesn't handle more than 512K. So we just have a one-liner hack that's in the core Linux kernel, and it's actually upstream in all of the Lustre server kernels around the world now, that just allows larger 1 meg IOs through. There was the same problem again in the Linux MD layer. And we've got a similar one-liner hack, and you know, the trick is fine, it's only a one-liner, but the trick is to find which line. So another thing I would point out, and then big thanks to Neil Brown for this one, who's giving a talk here this afternoon about RAID. He's given other talks at this conference too, is that we actually saw a corruption problem when we're doing RAID 6 rebuilds with a RHEL 5 kernel. I don't think any other site in the world saw this, like we never heard about it. But it was important for us, and this is one of the problems that took months to sort out, because we first had to figure out it was a rebuild that was doing it. We were only getting corruption on some small parts of the file system, the ones that had disk replaced, and then we had to find out which part of the software stack it was, and once we figured out it was actually MD doing it, then we had to find a reproducer. That took weeks to find a reproducer, and then it's kind of 24 hours for each reproducer run after that. But we eventually managed to get a git bisect down to some pretty large patches, unfortunately. And then we called up the Linux RAID mailing list, and Neil Brown fixed the problem within about 2 days. It was absolutely awesome. So that's now upstream in regular RHEL 5 and other old distributions that have this really old kernel and associated bug. So another thing that that's another one that I'll point out is that, so Lustre is a really big, complex file system, massively complicated network protocols, lots of parallelism for getting maximum speed and efficiency. But it is very hard to debug. I couldn't do it. There's a bunch of people around the world that can do it, but even they take months to debug some of these problems. So if you have something as simple as a race, in fact there was a get CWD race in Lustre for quite a long time, it does take quite a long time to fix it, and this is actually killing jobs, because it turns out that Intel Fortran's open call does a get CWD for no apparent reason. And so you have a job that's running in a newly created directory, it does get CWD, the open fails and the code fails. So all we did was like put a simple retry loop inside the kernel, you know, retry this 5 times, and after 5 times get CWD works and the codes keep on running. So it was vitally important for us to be able to hack the kernel around a bunch of problems until they're actually fixed. Okay, I won't go into the rest of those. So kernels, okay, so this is probably actually the main issue we have with kernels. We do have thousands of users, and they're running thousands of different codes, but they're doing lots of I/O, and we basically push the virtual memory system of the kernel quite hard. And we've seen a couple of instances of the kernel essentially tying itself in knots, looking for free pages. So one of these is easily solved by setting zone reclaim 0. If any distribution ships with zone reclaim 1, they should be shot. It's a terrible setting, has no merit. This was a similar problem that had the same symptom as zone reclaims, and basically it was the kernel looking in tiny memory zones, these 16-bit and 32-bit memory zones that are in every kernel you get from a distro. And there's only a few pages in these kernels normally, in these zones, there's only a few pages in these zones, but the kernel was spending infinite time just looping indefinitely in those zones looking for a few pages, when actually there was heaps and heaps of pages in the regular normal zones. So the simple hack is to just take out these zones from the kernel. So it turns out there's no config for this, you just have to get into the headers and set the size to 0. And then you just don't have these zones anymore, you're left with just normal 0, normal 1, because we got a two-way SMP. So there's at least one other supercomputer site in the world that did this independently of us. I don't think it's an uncommon thing to want to do, really who has 1632-bit hardware anymore. So it might be nice to have a config option for this one day in the upstream kernel. So I guess I don't have to talk about this. This is obvious, but it is absolutely vital to us to have source for the file system, the kernel, and every other part that we can of a machine, so that we can get in there and fix it. So kernel features that we plan to use more and more over time. At the moment, we don't use any of these, but we plan to use namespaces for a per job /temp on a compute node as a 200 megabyte RAM disk, and some crazy old codes have got /temp actually hard coded in there, not even using $temp dir. So they can fill up this. If we can set up namespaces, then we'll be able to let the resource manager control this and delete them. Also, lots of C-group features we'd like to use. CPU time freeze store instead of suspend resume. If you essentially have a fork bomb, then suspend resume has a trouble catching up and sending signals to all the things that are forking. Freeze store solves that problem because it's in the kernel, and we leave it that hard problem for it to deal with. We also plan to use memcg plus RSS plus swap instead of trawling the page table, polling it essentially every now and again from our PBS daemons. But memcg is still way scary for us because of performance implications. We haven't actually found something that makes it regress for us, but there's plenty of horror stories about the people who have, so we're going to wait a bit longer. So we would very much like to move to much more recent kernels than what we are. So we're kind of stuck with RHEL 6 kernels at the moment. We actually run RHEL 6 kernels on a RHEL 5 user land. And the new machine will be all RHEL 6. And the reason we would like to do this is because it's better. Like, there's a lot of fixes, especially in these zone things and the way memory is handled. We would have great confidence that a 3-point anything kernel would work with just about any distribution because of the awesome kernel ABI compatibility that Linux imposes. And the real hold-up for us is that the Lustre client isn't on these newer kernels, or it's very slow to get there. So if anybody from Intel would like to port the Lustre client into the mainline kernel, then this is a +1 from at least this HPC site. So a few minor Lustre topics to finish with. So there's been some talk on, I guess, the Ceph and Gluster folks in the last few days, saying that Lustre metadata is really slow, and certainly there is a design problem with it because there is only one Lustre metadata server, so that's a fundamental bottleneck, can only do about 100k IOPS at the moment, and that's a all software problem, so they can actually scale that up a bit over time. But it turns out that this is a whole other talk I've given, but it turns out that Lustre metadata is actually mostly bottlenecked when you do ls-l. It's actually bottlenecked on the data servers, not on the metadata server. So there's a simple Linux fix for this. It's to set VFS cache pressure 0 on all our Lustre OSS servers, and then all the metadata for the entire file system is always in RAM, and it's never slow. Unfortunately, there's a small Lustre bug related to this. If you create 1 million files and then delete 1 million files, then the number of D entries should go up and then down again, and on Lustre OSS it only goes up. So occasionally this is very manageable, especially if you have lots of quotas around the place. But I'd like to fix this one day properly eventually. So this is a final random thought. It's more of like a wish list thing. People feel free to tell me this is absolutely crazy and has no hope. But it turns out we have some crazy codes that essentially their workflow is forking and execing other codes. And that turns into basically a stat storm. So every fork and exec amplifies out to at least 50 stats across various file systems, usually to libraries. And frankly, they're to libraries and applications, so it's not as if we can cache the operating system on a node, or that would actually fix the problem. So what I'd like is that if we could have a hack to the VFS on the compute node client, so we had essentially local VFS performance with global file systems scalability and management. And my best sort of what I've seen out there that's closest to that at the moment is something that's based on the Fuse style state cache with a large timeout. So basically, if you see that your file is on a read-only file system, you go and stat it, but you don't stat it again for another 60 seconds because it's a read-only file system. And we can do this because we control the read-only file system. It's a safe thing to do. If we want to update anything on our read-only file systems, we just set this timeout to be 0 seconds instead, update it, and then set it back to 60 seconds, and there's no coherency loss across the cluster. So yeah, it'd be fun to try it out, but feel free to tell me it's not going to work for all sorts of reasons. And that's all I've got today. Thank you.